In this video, we're going to do a second example problem using Archimedes' principle. Archimedes' principle concerns the buoyant force or buoyancy force acting on an object immersed in a fluid. In this figure, I have drawn an object which is surrounded by some fluid, and the squiggly arrows represent the action of the pressure in the surrounding fluid on the object. The buoyancy force is the net force exerted by the pressure in the surrounding fluid. That buoyancy force would point upward, and according to Archimedes' principle, the magnitude of that buoyancy force would equal the weight of the displaced fluid. In other words, the buoyancy force would be equal in strength to the weight of a blob of the displaced fluid with the same size and shape as the object. So here's the example we're going to do. We have a container which has a layer of oil on top and a layer of water on the bottom. The oil is less dense than the water. And what we have here is a wooden block, and the wooden block is kind of floating at the interface between the water and the oil. So the wooden block is sticking partially into the water layer and partially into the oil layer. Now, if the wooden block was more dense than the water, it would sink to the bottom of the water. If it were less dense than the oil, it would float to the top of the oil, but it's doing neither. It's just hanging out at the interface between the oil and the water. And that tells us that the density of the wood is somewhere between the density of the water and the density of the oil. And we would like to figure out what is the density of that wooden cube. So I would invite you here to start the problem by drawing a force diagram for the wooden cube. And if you can, include in your force diagram expressions for the magnitudes of the forces. And once you've had a go at that, rejoin the video. So here's how we draw a force diagram for the cube. First, let's put in the gravitational force. The magnitude of the gravitational force would be the mass of the cube, so C for cube, multiplied by the free fall acceleration, little g. And then we have the buoyancy force acting on the cube. According to Archimedes' principle, the magnitude of the buoyancy force is equal to the weight of the displaced fluid. In this problem, we have two displaced fluids. We have displaced oil and we have displaced water. So the magnitude of the buoyancy force will be the weight of the displaced oil plus the weight of the displaced water. So I'm going to come into the figure here and put in that magnitude. That's going to be mass of the displaced oil. So DO for displaced oil times little g plus mass of the displaced water times little g. Now, before we proceed with the calculation, let's do as usual and put in a y-axis. So now we want to find the y components of these forces, and I'm going to do things a little different. Instead of drawing the grids like I usually do, I'm just going to write out expressions for these y components. So to start with, we have the y component of the gravitational force. Since the gravitational force points in the minus y direction, its y component would be the mass of the cube times little g. We have seen earlier in this module that the mass of an object is equal to its density times its volume. So I'm going to replace the mass of the cube with density of the cube times volume of the cube. Then we have little g. So what would be the volume of our cube? Well, the area of that top face is A. Now that area is actually going to drop out of our calculation at the end, but we're going to use that area in the intermediate steps. So the volume would be this area A multiplied by the length of this edge here, which would be d oil plus d water. Okay, so volume gets replaced with area and then times d oil plus d water, then times little g. Then we need the y component of the buoyancy force. Now the buoyancy force points in the plus y direction, so its y component would just be the magnitude. which would be mass displaced oil times little g plus mass displaced water times little g. Again, we're going to use that mass is density times volume. So the mass of the displaced oil would be the density of the oil, rho sub O, which is given here, 0.8 grams per cubic centimeter, and then times the volume of the displaced oil. Now, we'll have to think about that a bit. So I'm just going to leave this as V sub dO for now. And then we have G. So all of this is the mass of the displaced oil. To that, we add the mass of the displaced water, which would be the density of water, 1 gram per cubic centimeter, times the volume of the displaced water, and then times, again, little g. So all of this is the mass of the displaced water. Now, what would be the volume of the displaced oil? The volume of the displaced oil would just be the volume of that portion of the cube which lies above the oil-water interface. So this region that I'm outlining in green here, this would give us the volume of the displaced oil. Now notice that this region has a surface A, but then only a depth d sub O in the vertical direction. D sub O is given as 4 centimeters. So the volume of the displaced oil, I'll put it over here, would be that area A, and then times dO. Now, what would be the volume of the displaced water? So the volume of the displaced water would be the volume of this region here. In other words, the portion of the cube which sticks below the interface. Now, what is the volume of this portion of the cube down here? Well, the volume of this portion of the cube would be, again, that same area A multiplied by that vertical edge of that lower portion, which is d sub W. So the volume of the displaced water would be A, and then times that dW. So let me use these expressions here and here to rewrite volume displaced oil and volume displaced water. So that's going to give me, for my first term, density oil, then volume displaced oil is ADO, and then we have G plus, now working on this term, density water, volume displaced water is ADW, and then G. Now to wrap up the problem, let's sum the y components of the forces to 0. We only have 2 forces, the buoyancy force and the gravitational force. So summing the y components of the forces to 0 means that we have gravitational force y component plus buoyancy force y component equals 0. So let's take these expressions that we got here and here and substitute. So y component gravitational force we found over here is minus density cubed times area times d oil plus d water times little g. And then we add in the y component of the buoyancy force. Now, this is a lot to write. And notice that these two terms have a common factor of a times little g. So I'm going to pull that out. And we have a times little g times density oil, d oil, plus density water, d water. All of that equaling 0. So now we can solve for the density of the cube. So it's a couple algebra steps. Notice that both of these terms have area times little g. So we can divide through by area to cancel the a's, divide through by little g to cancel those. Now we're almost there. Let's take this expression in the parentheses here and move it to the right side. I'll just do that as a single algebraic step. So I then have minus rho cubed times d oil plus d water equals, putting this on the other side, minus this expression, density oil, d oil, plus density water, d water. I can cancel the minus signs against each other and now divide through by d oil plus d water. So I now isolate the density of the cube as rho oil, d oil, plus rho water, d water, all over d oil plus d water. So substituting now, I have density of the cube is density oil, 0.80 grams per cubic centimeters. DO, 4 centimeters plus density water, 1 gram per cubic centimeter. DW, 6 centimeters. All of that over DO plus DW, 10 centimeters. We have centimeters in the bottom, which cancels centimeters in the numerator here and here. So the only units that remain are grams per cubic centimeter, same in each of the terms. So the unit of our answer would be grams per cubic centimeter, as we would hope. And then numerically, I get 0.92. So the density of the cube is 0.92 grams per cubic centimeter. And now we have solved a second example problem using Archimedes' principle.